Hello folks. My name is Shayan Ghosh. I work at PNNL, and I'm one of the technical co-chairs with Rohit Sambre and Ryan Grant. And I welcome you at Hot Interconnects, the tutorial session. And I'm very glad to to introduce this tutorial on telemetry tracing, profiling, analysis, and performance of workload offloads on Intel Scalable Processors with Integrated Accelerators. And the speakers, we have speakers from Intel who are Mrittika Ganguli, Karthik, Raman, and Kalyan G. And this tutorial will provide an overview of the Sapphire Rapids processors, highlighting their features, performance improvements, and integration with accelerators. And the brief bios are Mrittika is a principal engineer and director, cloud native pathfinding in Intel's network and edge architecture team. And she has about 25 plus years of experience in cloud hardware and software management, network storage processing, telemetry, QoS, scheduling architecture. She has an MS and CS and 50 plus patents and multiple IEEE papers in this area. Karthik is a technical expert with more than 20 years of expertise, 5 years at Intel in network architecture and cloud platforms. He's leading the solutions for telemetry architecture, accelerated computing, SmartNICs, in his present position as cloud solutions architect. And finally, Kalyan is an accomplished technical expert with more than 20 years of expertise in cloud platform architecture. He's leading the solutions for accelerated computing in his present position as cloud solutions architect, about 10 years at Intel. And so we are very excited to learn more about the upcoming, the new Sapphire Rapids architecture. So take it away, folks, and welcome to the participants.
Thanks, Shayan. Sorry. Now I want to start sharing, Mrittika, or you're going to share?
Go ahead, share.
Okay, 1 second.
So while you are sharing, I'll just mention the Slack channel where folks can ask questions, but feel free to ask questions in the Zoom chat as well. I guess that's okay for the speakers, right?
Yes, it is okay. So we have divided up the presentation such that we go over in a certain cadence and we can stop and take questions, or since this is a big flow, so we'll try to take questions towards the end. So I think we kind of agreed it's taking questions, answering them towards the end is a better idea. But please, please post the questions.
All right, thanks, folks. Please post the questions either on Zoom chat or on Slack. It would be, both of the platforms would be monitored. Thank you.
Thank you. So thanks, Karthik.
Are you able to see my screen? Everything is fine? Yes. Okay, great. Yeah, go ahead, Mrittika. All yours.
Okay. So let's go ahead to the next couple of slides. We have to show disclaimers because we're showing performance data. It's largely around workloads and the accelerators on Intel 4th generation processor. So what is our agenda? Next slide, please. What we will cover here is telemetry, why it's important. What are the use cases that generically in a data center and edge environment that that telemetry use cases apply to? What are the kind of frameworks we have within Intel platforms, roadmap of processors, just to get you up to speed of where we are. The larger focus of this presentation is on accelerators. And we introduced multiple accelerators in Intel 4th Gen Xeon. And so we'll cover 2 accelerators. One is Intel Dynamic Load Balancer, And the second one is Intel Quick Assist Accelerator. We'll actually do a step-by-step walkthrough on telemetry collection, analysis of the QAT or the Quick Assist Accelerator with the RocksDB deployment. Next slide, please. So today's workload demand fast telemetry, and why do they? Because in many of the deployments, we have fast I/O requirements. The data center workloads nowadays have very short duration communication patterns that are very, very latency critical. Largely due to the deployment of microservices. And it's much more difficult to optimize these workloads than it was in the past. There is a need to have stringent SLAs. And so cloud providers and edge providers are trying to figure out how to operate their servers in low utilizations and improve their tail latencies. To be able to do that, we have to be able to predict much faster what's the root cause. And for that, we need faster telemetry. In addition to faster telemetry, if we have multiple entities on the CPU, how do you manage the performance and power using this telemetry? How do you collect telemetry at different at the different feature sets that we have on the CPU? How do you process that? Especially if you have microsecond scale I/O, there is a tension between performance and productivity. And so how do you manage all of that? That's one of the big areas of work that we have. And then within that, our Intel SoCs have immense amount of on-die telemetry. How can we use some of that? When we are introducing new accelerators, how do we manage the base SoC telemetry and also the accelerator telemetry to be able to give you a picture of how much do you need to tune your performance, how much do you save if you are using an accelerator, how much do you save, when do you need to offload to the accelerator, which is again an on-die accelerator, and when do you continue to use your application CPU cycles. So that's the landscape. A very good paper on attack of the killer microseconds is something you can refer to on what is the problem statement of the microsecond performance need and how telemetry can actually help in that. Next slide, please. So what are the telemetry use cases that are out there? And some of the usages that we'll show will actually map to some of these usages. At a very basic level, you have power and performance. So measurement of power, improvement of power management for the optimal performance you need. And there are not just telemetry, but control mechanisms already inside the CPU. You can have faster telemetry prediction at a basic level. And then you can stream out and do at a larger level. Another big usage, which is largely there in the client side, is security and user experience. How do you manage, data DDoS kind of environments, and also not have a bad user experience? How do you detect hardware and software side channel attacks? A very big usage is at the data center, which we started with, and our focus will be at the data center in the next few slides, is latency critical microservices workload. Proxies that come in front of microservices to front end the application. What kind of telemetry can we look at, and what kind of optimizations can we do? A fast, intelligent telemetry drives the utilization, because at the cloud level, application users and deployers, they want to manage TCO. And so they want to manage how much performance you get out of the CPU instances that are getting utilized. So these are some of the usages that we will focus on, especially the last one on data center utilization and efficiency. Let's get to the next one. And so here we show you the just to baseline. Some of you may be aware of previous platforms We just want to put that in a picture of it. The platforms which are out there since last year, Ice Lake, the Whitley platform, Ice Lake, which is our 3rd generation with basic enhancements to PCI Gen 4, crypto acceleration. We have crypto acceleration at the ISA level. We have AVX 512 based crypto acceleration. We have another security entity called SGX, which is for secure enclaves. And then we have other NVMe and other IO devices attached to that. We launched Sapphire Rapids, or 4th generation, this year. And this comes as part of the Eagle Stream platform. And we'll have 2 CPU platforms. One, Sapphire Rapids, is already launched, and EMR or Emerald Rapids will be coming up end of this year. And they both are targeted to microservice environments and application environments in the data center. And with Sapphire Rapids, we introduce a host of accelerators in addition to CXL and Gen 5 and other DDR enhancements. The accelerators listed on the right-hand side are QAT for Quick Assist Acceleration, which helps in crypto, compression, and a few others. DSA is another accelerator for data copies. One accelerator not mentioned here is DLB, which will be there only in certain SKUs, and that's a load balancing among cores accelerator. TDX is an enhancement over SGX, or a different implementation of secure enclaves, and that gets started in EMR. And another set of CPUs that are coming out early next year is the WordStream platform. And there we will have one kind of platform which will have efficient cores, which will be single-threaded cores, but a large number of cores. And those are the Sierra Forest and Clearwater Forest. Whereas there will be another CPU called Granite Rapids. It will be a performance core, but the platform architecture is similar. And they will both support different kinds of workloads. The base platform telemetry will continue to be backward compatible plus new ones. And we'll cover some of the CPU platform telemetry in the next few slides. And now I hand it over to Kalyan.
Yeah, thank you, Mrittika. I think good introduction for that part. And as we see from the SPR onward, we added an accelerator on the chip, on the die. And so this, we will talk about on that here. So what we are talking here, that we have added 4 new accelerator on die of the SPR itself. So it's not in discrete somewhere, or it is not on the core. It is on the die in close vicinity of the core. And so within this, we can see a picture that there are 4 accelerator complex, and every accelerator complex hosts 1 instance of each accelerator. So we have 1 instance of DSA, DLB, QAT, and IA in all 4 accelerator complex. So at the best, you will have 4 instances of each accelerator in a SPR system. What I was mentioning, that this is to highlight that this is not on the core, like we have seen in AMX, but it is on the die. That make this accelerator very easy to operate, to offload the functions, which are very common and critical in the normal cloud workload, very common workload, and they happen very close to the CPU. We are not delegating it to somewhere in a discrete far away, but very close to the CPU. And the benefit of this here is that, as Mrittika was explaining, when we do the telemetry and we know that certain workload which is best suited for CPU and certain workload which need accelerator, the telemetry information can quickly give us, and we can smoothly hand over that work to accelerator. And when we find that accelerators are not required in some case, you quickly come back to the CPU. So this soft handshake between CPU and accelerator give us the ultimate power to realize the capacity of this Sapphire Rapid. That's why this become a kind of secret secret capability which can be explored without any additional software cost because it is within that. What is important to know that here we trying to upload most the common operation, and the idea is that when we upload that operation, we free up the CPU to the most cost-effective or valuable operation which CPU gets sold for, and that way the effective benefit which CPU end customer will get, their effectiveness goes up by big time. And it's all within the die. So that's the beauty of this accelerator. So maybe next slide, we'll just see what are these 4 accelerators to understand. So Mrittika also touched on that we have 4 on-die accelerator. And first of them is QAT, the quick assist technology. And we selected this because we see a lot amount of data exist in the data center, and if we can compress that data to the best capacity, that give us the best return of investment for us and for the customer. So first thing we have built is the data compression, big time data compression accelerator called QAT. And here we support multiple type of compression standard, most of the industry known compression standard. And also along with the data, these data, when they move, we want to encrypt this data while on the move or on the storage. So this accelerator provide encryption, all type of encryption, and then all type of compression capability into this accelerator. And so anything on the CPU, wherever we see compression requirement, we will offload that. We will see further on that, some demo on that. And second accelerator we have is a data streaming accelerator. What we all realize that we have data in the data center and we have a lot of compute to be happen on data center. But for these two to perform best, this data need to move from one place to another place to happen. So there is a lot amount of data operation, copy operation, move operation, fill operation in our happen in our system. So idea of doing this is to develop accelerator where you can offload this function within the CPU die. It's not going anywhere in discrete, so not cutting your latency or anything. And it is getting uploaded on an accelerator within the die. And then you can free up the CPU from this activity and CPU can perform more computation. And overall performance of system will go up. So the DSA is exactly targeting that. It's very lightweight, easy to use accelerator. We can replace the mem copy from normal memory to a DSA memory things. And then third one, which we have, third and fourth, which are pretty little bit a specialized accelerator, like we call IAA, in-memory analytic accelerator. So as the name goes, analytics, which is happening on in-memory. In that case, we need little different kind of operations. So we need high number of decompression engine there. So we focus here on that. And some of the scan, filter, analytics, common operations. So that can be uploaded here and that give overall performance improvement for this kind of workload in that. And the last one, which Mrittika will talk later, is the dynamic load balancer, which call. As we saw in the network, huge amount of packet and processor happening. And so managing them, the queue is very important. And also balancing the queue to effectively utilize your CPU can improve the performance of overall. So DLB is exactly targeting that operation for a specific workload on networking side, and that then it will offload that work. So as we see here, one other thing I wanted to mention here, since all these accelerators are built on die, it is utilizing the lot of infrastructure of CPU itself. So the data to move the data from CPU to accelerators are pretty efficient. So this is a big advantage whenever we see accelerator, if it is discrete accelerator or other one, this make this accelerator very useful and very effective. Another point to note that we have already listed 5 platforms here, SPR starting, then Emerald, and then Granite Rapids and Sierra Forest and CWF. And we see once we go to the next generation, we have enhanced the performance, gen-to-gen performance, and also added new feature as it become more relevant during that time frame, so that make this accelerator a leading accelerator to support most of the critical use case here, and making the CPU utilizing this accelerator the very powerful CPU. So yeah, that's the intention. So maybe we'll go to the next slide to see if very quickly we want to say where you will like to utilize this, if we want a quick one-page slide. So if we are working in infrastructure where we have a lot of memory movement operation to happen at kernel level or host level, and then of course in a storage and networking where again we move a lot of data. So DSA definitely you should consider. Second thing, as we compress the data, whether in the storage or in the networking and also in the analytics, big data analytics, particularly compression and decompression become very important. And so QAT should be considered there. Apart from that, as we move in the network, that all the data need to be encrypted. And one more feature we have here is called public key encryption. That means when we are setting up the connection between the two network, you will need to secure that network, and the PKE provide that offload capability. So that to map, and the DLB, as we mentioned, it is a queue manager. So in networking use case, this will be very effective to use and save the performance. And in-memory analytics, IAA should be utilized in in-memory database, whichever we have open source or otherwise in-memory database, key value database, other one, we can utilize this and gain a lot of performance gain here. So yeah, that is in simple how we will position this 4 accelerator. And yeah, now probably move to Mrittika for the more. Over to you, Mrittika.
Yes, thanks. So let's start off on the telemetry architecture. What do we provide? So as you see here, this was introduced in stages in Sapphire at a platform at a board platform level. You can it is just showing 2 dies right now. Essentially, you can have a management controller. It could be a BMC or any other management controller that can give you a separate out-of-band management port. If that's there on your server platform, how would you use a telemetry architecture for streaming out some of that data? So what this shows here is a tiny block called OOB MSM that you see here. It's out-of-band management entity, which can be used for getting the data out of the CPU microchip and other entities and streamed out into the BMC, and then the BMC can help you stream out to an application. So what does the OOB MSM have? It is microarchitecture based. It will essentially allow you to do 2 things. The basic performance counters that are out there, you can have simple software entities called aggregators to aggregate that telemetry of the multiple IPs. And then you can have other software entities which will basically watch the aggregator data. Instead of trying to watch all the CPU counters, which can be in thousands of, based on each platform, they can be thousands. You can have a slightly higher level ones at the aggregators, and then establish watchers to watch on the aggregator data. This helps us reduce the amount of data going out. And then it also helps in the use cases, implementing some of the use cases down at the host level. So this got introduced, and if anyone is interested on how to write aggregators, watchers, we can work separately on how to do that. But this gets introduced at the platform level. And the communication internally MCTP based, so you can configure it through the management port through MCTP. And BMC is always connected, configured through the NIC using the MCTP SM bus. And so this is largely showing the connectivity internally so that you can assess how much would be the latency of data travel within that. And does that fit in your use case or not? So this is like an overview of that. Let's go to the next one. Okay. Now we are going a step further where we want to showcase where do you start with telemetry at the CPU. Now, what we have done, and you may be already aware because this is a solution which was introduced a few CPUs before, I think somewhere from Broadwell onwards, that got introduced. And so this is called TMAM, or top-level monitoring architecture. What it does is, at the CPU level, if you have simple metrics like those that you show in brackets here, like micro ops retired, or CPU clock unhalted, or TSC. These are very minute measurements at the counter level. What TMAM does is it doesn't aggregate, but it gives you a different view. And there are 4 or 5 pillars to TMAM. It can tell you whether your workload is front-end bound based on a slew of counters that are out there. The front-end bound metric, basically, it represents a fraction of the processor's front-end to back-end communication. And it will tell you whether whether you have, for example, if you have an Nginx proxy or an Envoy proxy, you will see them initially be front-end bound because they're just trying to send requests, and the requests are getting forwarded to different other software entities on the CPU cores. When you start a workload which is more compute intensive, you will see that being more back-end bound, and that means it's largely either your CPU utilization is going up. You'll see if it is back-end bound, you'll see CPU utilization going up, you will see memory usage going up, retiring of operations happening more. Whereas in front-end bound, you can also see whether there are more branch mispredicts happening, there are more bad speculations happening. Is there higher latency at front-end bound? If you see low CPU utilization overall for your application, you can first focus on the TMA section or TMAM section of the performance monitoring counters to shortlist, where should I look at? Should I look at the front-end bound counters and find out where the bottleneck is? Or should I go look at the back-end bound and find out if it is CPU or memory bound, or it is cache bound, right? Or if there are heavy operations. Now, this is something we use a lot in our own analysis, and I'll show sometimes, and this whole architecture is changing a little bit. Sometimes TMAM may or may not be able to give you a clear picture, and I'll show an example of that. And then what other metrics can you look at, especially if you have a network workload? What can you look at? Okay. Let's go to the next slide. So here I'm directly jumping into introducing a device under test environment. Essentially, we wanted to show you 2 things. One is a workload, a network workload, like a proxy workload, like Envoy. Envoy is a data plane of a proxy environment in the data center. It can be deployed as inside an ingress gateway, like an Istio ingress gateway. It can also be deployed as a service mesh. So the Envoy data plane will be inside an ingress gateway, plus in what we call sidecar applications that combine with the actual microservice. And a service mesh generally helps you in scaling your application, providing secure policies, and also monitoring and visualization of your data. So in this environment, this is a very simple setup. It shows a client running on a worker node. The benchmark tool that we use is called Nighthawk. This is an open source tool. We have Nighthawk client or worker running on one system. And the server under test is a Sapphire Rapids server with the Kubernetes deployment, with the Istio ingress gateway, and a very simple microservice, which is the Nighthawk server, with the Envoy proxy as sidecar. So Envoy proxy is in both the ingress gateway and in the sidecar. Our goal is to see how does the performance of ingress gateway vary as you increase performance. And we have 25 pods going up to around, I think, 100 pods. So we are taking different kinds of data sets, 1 kilobyte, 10 kilobyte, 1 megabyte. And we'll show you one use case where we keep the number of client threads constant. So 40 threads means 40,000 connections to the gateway. We'll keep the initial throughput in requests per second also constant, and we look at latency. And we, for deployment of 6-core, 12 threads, the Ingress gateway is right now using 6-core, 12 threads. We have a detailed benchmark around this, which we can, which we have open sourced, and you can take a look at that gateway, whole data point around scaling, of course, and other things. But for here, we'll just look at latency, and let's go to the next slide, and I'll explain how we do the latency. Okay. So here what you see is essentially on the left-hand side, you'll see largely the requests per second. The requests per second here for 1 kilobyte, 10 kilobyte, 1 megabyte, and mixed meaning it will have all these three. And they are kept constant. So we have two usages where we are running it first with a set number of max requests per second. And so for each data set, the max that it reached is, for example, 7,000 for 1 kilobyte and 7,000 for 10 kilobyte, whereas for 1 megabyte, it goes down to almost 2,400. And we look at the latencies that each of these different data sizes give. For the mixed one, you get around 6,000. And then we have used the accelerator DLB, which is a dynamic load balancer. It helps you in load balancing the traffic, the Ingress gateway traffic on the worker cores. So 6 cores, it may have, I think, 6 worker cores, 6 worker threads, or it might have, double 12 worker threads. So, and this was a problem statement that exists in all HTTP proxies. We have the same solution with Nginx too. Now, what we see is that as soon as we use DLB, we can improve the latencies, which is on the right-hand side, improve dramatically, especially for the mixed workload. It is about 90% reduction. In this whole usage of this accelerator, the largest benefit is to latency. Since we are keeping the RPS same, and we are not increasing or decreasing, the utilization doesn't change much. If you see the utilization table on the left bottom, the utilization doesn't change much, but we have reduced latency. And we are using these metrics to figure out, the goal is to reduce latency. Now, if you want to improve utilization, and then you could actually drive up the requests per second. And then if you try to drive up the requests per second, your latency reduction may be lower. It may not be 90%, it may be 30% or 40%. And you can take that goal. Again, you'll have to use telemetry to decide, okay, I have 50% left on my utilization. Let me drive up the RPS. These goals can be taken. Now, we provide metrics to allow you to measure and then change your goals. If you want latency, you have this experiment here. We have other data points to show you can improve latency utilization also. Okay, let's get to the next slide. Now here, I wanted to show you the CPU metrics and what makes sense and what doesn't make sense. So for example, the first few are on, the first 3 are on operating frequency of the CPU. You can see that without the accelerator and with the accelerator, there is about certain percentage improvement in both frequency. Utilization, there is not a whole lot. At a 6-core deployment, it is largely 2% improvement in CPU utilization. The CPI improves certain percentage points, but others like the TMA, which I was talking about, front-end bound, back-end bound, does not change much. So it's not giving us, if we just look at the TMA metrics here, it will not give us an idea of what this workload is dependent on. However, we have not exercised all the different ways, and so we go ahead and look at the IO metrics. And I have outlined 4 IO metrics. There are others also which show large difference and which will also help you in characterizing your workload. So in this case, the last 4 shows that if your snoops are going up a lot in comparison to a different workload. Now, how do you know if your snoops are a lot? Well, in comparison to other workloads, if your snoops are going up, like here, you will see the snoops are low. They are blocked in conjunction with a remote char occupancy, the IIO buffer occupancy, and the PCI read-write current data. So these are 4 metrics which are going to tell you if the queues of different entities of the CPU are getting blocked. And you'll see a difference with and without DLB. It shows that the queue blockage is removed as soon as you add a hardware accelerator like DLB. They come down quite a bit between the chart or occupancy, the IIO, and the read-write current read-write. You'll see large differences in that. And this is a particular workload. From these 4, you can deduce that, yes, DLB is helping in latency improvements. So this is one usage of the EMON that I wanted to bring out. And there are many others, and I'll encourage people to go to our website and look at other usages of Envoy, where we show QAT-based and other accelerator-based EMON, where the TMA will give you a clear picture. Okay, I'll hand it over now to Kalyan.
Yeah, okay. Thank you, Mrittika. So yeah, coming back to some of the other accelerator, the QAT. So we took an example here to showcase a database applications where the QAT accelerators, how it could be applied and how it get applied. So RockDB is a very famous storage engine for database, as we know. And this we selected because this get deployed by many other database applications like MySQL or MariaDB. They will use this as a storage engine, and then database will sit over that. So that example to show that. And as we see in this picture, just to highlight that where and all accelerator intercept. So when we start from the writing point, when we get the data into memory, we start putting into mem table. And as that get filled, we can't store in more on that. So then we need to flush that data into a bigger storage device in SSD case. And in the RockDB case, the format uses SSD format, but in that format. And you just see here, when we move data from a memory DDR to a storage device, here we will like to compress the data so that we require less storage space when we store it. That's the first step of that happening. And then as these data reside on a storage for some time, you will analyze the data for better, because in first case, you have quick time to response because you want mem table to be freed quickly. In second case, you can analyze the data a little better, and you can do a compactness exercise. That means you will compress the same data to a higher level of that. So we will use a decompression because we want to decompress it, and then compress it again, and so that we get higher compression ratio into that. So it reduce the size further. That's what it means, and that's a typical exercise we do. So that, and when we want to read this data for consumptions of data analytics, that time from that SSD, we would read this compressed data and take to the cache of that. And in that process, we will need to decompress this data and put it there. So what we see in the whole process, there are multiple time compress and decompression happening. And in all this position, QAT will come handy. So whenever we are compressing from memory to storage, or doing compactness within a storage, or when we are decompressing from SSD to block, in this process, QAT as accelerator is available within the CPU die, not going anywhere else, to offload this feature so that CPU get better to do that. Yeah, so this is a typical flow, and many use cases follow the same flow. So idea to show an example of that nature. So one more thing, as we know in the compression world, that when we develop a compression standard, we develop try to put the whole lot of computation portion into compression engine. And yeah, you can be here. So that we make a decompression lighter, because it's normal practice that when we need data for use, that time we need that quickly. And that quickness can come if we have lesser computation to be done at decompression level. And so that when we design the compression, I work for quite some time in compression for 10 years. So that's why I'm talking a little more. So whole efforts are put into the IPs so that compressions are designed complex enough, and it takes as much computation as possible, because latency is not that big concern when we are compressing. But idea is that make decompression so light that it is very useful when these data are needed. So I am trying to share that if we want to take a lot of benefit of computation offload, let's focus on the right portion of the data, basically the compressed portion of data here, just to showcase, and let's see how QET is impacting here in this case. So for this example, we took a simple RockDB case with write-only things, and we let the RockDB change the instances to meet the 99% utilization of the CPU, so that we try to get max it can get. And we took this thread for background flush operation and the compactness thread, as we mentioned here in the picture. And for comparison, we did it with the LG4 compression standard. I know in the cloud world, 3 compression standards are very famous: LG4, G standard, and deflate. So we took LG4 and QA and the G standard and compared with the QET capacity here in this case. For example, we took a 16-byte key size and 2-byte value size for a 16 kilobyte block size operation. As you know, in practically, it could be 4, 16, 25, 256, higher it can go, all that, but for this example. And on the hardware security, in our SPR side, what we have 56 core SPR platform, which is publicly available today. And we use we had 4 instances of QET here in available, as we saw in the previous diagram. And we took the available QET chip, which is available with the QET hardware, a version number we gave just for in case we are comparing, because software keep changing. And we use L1 compression, level 1 compression. For all the data analytics portion, we will generally use L1 compression. And for a storage application and other things, we try to use L9 compression. In the compression world, that's how we use it, where we know it. And for comparison, we use a standard G standard level 3, which by default did get used, and default LG4, which get used for RockDB use case. I'd get used by RockDB. And that's the landscape to comparison. So next slide, we'll see that if we do in this case, what kind of gain we can see here. And to make this slide look very simple, what we did that, okay, let's maintain a constant throughput so that we don't try to put you too many variables here. So throughput here is the operation per second for your database we see here. So we have around 10 million kind of throughput operation try to fix. So suppose all 3 have to attain same throughput, what would they achieve? So that's why the throughput line, if you see, it's trying to look constant, because that's purposely we did that, so that we compare. You can always keep one variable fixed, other variable changing. And as we see in this case, when we use G standard in the software and when we use LG4 in software, we saw 2 deviations here. LG4's data size is very big compared to G standard. As you see, LG4 data size is 456 megabyte and G standard is 349 megabyte size. So what it means that you need more storage space and memory space if you're using LG4 for same thing. And yeah, that's one thing we see here. So, and another thing we see here that to have G standard this kind of throughput, we use 88% of the CPU utilization, whereas in LG4 we took less one, and that indicate that LG4 is less computation intensive, is focusing more on getting higher throughput by compromising on the data size, whereas G standard is focusing on getting good data size but letting a lot of CPU computation happen. So that's how it is designed fine. So when we offload this to a QAT L1, getting same throughput, what we can see that if we are using LG4, first thing you can see that we can drop the data size from 456 to 367. That means around 25% extra. You save additional compression, you do it here. And when that is available to us, that will help reduce the memory cost, the storage cost, the networking cost to transfer the data, and overall cost in the performance. Second thing is that when we take with respect to G standard, because here we were taking around 90% of the CPU, that itself be choking. When we offload to a QAT L1, we will only require 54% of the utilization. So around 33% of CPU get saved by maintaining same throughput. So that means if you have additional 37% CPU available for you, multiple things you can do. We can free up the CPU for other workload. We can improve the performance per core because now we have less computation requirement here. Second thing, we can increase the throughput. Here I try to pick fifth throughput, but now we can have 33% extra throughput when we use QL3. And when all these things happen, we can decide to build a database which can support larger database now because we can do 33% more work on that, which earlier would not have been done. Yeah, that's one thing just to highlight that. And one more thing which I probably didn't touch it, that QAT accelerator have a capacity of supporting 160 gigabyte per second in SPR. That's a huge number, which we will not be even able to achieve even if you apply all 56 core of CPU. So you will need multiple socket of SPR CPU. So that give us the capacity to build higher amount of database when we use accelerators. Yeah, I will leave it at this. Any question, of course, we'll answer and then hand over to Karthik for the demo on this.
All right. Thank you, Kalyan and Mrittika. That was a very, very informative talk for probably most of you guys have seen. But let's see some of this in action right now. So what I'm going to do over the next 15 minutes is to show a live or real-time demo of how we are using RocksDB, how we have deployed RocksDB on just CPUs and then offloaded to a QAT engine, and what kind of performance benefits and details are you going to get, right? Okay. So similar to what Kalyan mentioned, I'll be doing I've done an install of RocksDB on a CPU core only, and then offloading that to QAT engine, and how we are capturing telemetry, what kind of utilization improvement are we getting, how many CPU savings are doing, what kind of latency improvements we see. We're going to see that in the next 15 minutes or so, right? I'll go into the demo straight away in interest of time. I'm going to change my screen right now. Second here. And I'll start sharing again. Okay. I hope everybody is able to see the screen. In here, I don't know why this keeps coming up. Okay, great. So in here, I'm running a simple RocksDB application on Ubuntu system with Sapphire Rapids with the kind of a QAT accelerator, and I'm running a script called dbbench. So dbbench is the benchmarking tool that is used by RocksDB for measuring performance against certain all the use cases. In here, I'm using a 16K key value store with a 256 byte write only using Z standard compression methodology. And as I kickstart that script, you can see the telemetry is getting enabled, and this will start progressing towards what I call 1 second. Yeah. So we also have like Grafana installed. Here you can see there is a process that is getting kicked in by the CPU. And you can see something called, I want to take a minute to spend on this particular slide here. You can see on the right-hand side, there's a big list of CPU numbers with mention of the different latency data. So this is basically how much time is spent on each core when the data is coming in, right? And that is a time that you'll see as the operations or runs start to progress. This time is going to vary over the next few minutes, right? And also you can see the CPU is right now extremely low. It's probably about 11% utilized. There's not much utilization happening. So I will continue with the flow. Yeah, now I've kicked in a script for the DB bench. And here you can see it started to do a fill sequencing status. Basically the DB bench workload or the benchmarking services doing a fill sequence, and it's doing against for about 500 seconds, which is about 3 minutes interval. And it's going to do the sequencing operation. And I will show you the logs in the next few minutes and how we are capturing telemetry sort of a thing. And when I do a head stop, you can see there is a very, very low utilization. There's about 2 processes running, and there's absolutely no kind of no our compression or decompression activity happening at this point of time, right? As you progress forward, screen is... Yeah, now the process is kicked in, and you can see the CPU going almost about to 94%. So as the process got kicked in, and you can also see the latency now is going to increase significantly. Here you can see the latency per CPU core is almost hitting like 900 milliseconds or 1 second in some cases too, right? So this is a very high in terms of the latency happening. This is per core latency that's happening at a processing level, at a processor level. And you can also see the CPU kind of getting busier as we kind of progress forward. So the load also goes up, the system load goes up, the kind of latency goes up too, right? I'll move again. And as I progress forward, one thing I want to show is a very interesting output here. 1 second, I was at 431. Yeah, I'll take a minute here. So here you can see the encryption work is started, and it is doing a write function, and it is also doing a compression using Z standard, as you can see in that highlighted line. And it is using the key value store size of about 16K and a value size of about 256 bytes, and the block size of about 16K sort of a block size right now. And it is doing typically a write function. 100% of the function is happening right. So that's the status you're able to see right now. And we'll slowly move forward with this. And as you see, the latency continues to increase. And sometimes it's going almost 1 second or 1 millisecond, close to about 950 milliseconds sort of a thing, right? The operation is still running. It's waiting for the run to complete right now as we speak. And once the run is completed, you will see the output of the value coming in shortly, right? I'll quickly jump to that. It is still running. It's running about 96% right now. Pretty high in terms of CPU load. Since I've set the timer for 3 minutes, so it is taking a longer time for the run to complete. So in the interest of the demo, I'll continue to move forward with this. Yeah, now the run is completed, and it is, as you see, there's only 2 processes running, and the CPU utilization is now dropped to almost 0% or less than 0, approximately about 1 to 1, less than around 1% sort of a thing. And you can see all the compression activity is now stopped on the head stop process, right? and I'll move forward. Yeah, now the test is completed. You can see there's a throughput value of about 18 million IOPS has been achieved. And the data size is about 358K. And the max CPU utilization that it touched was about 94%, right? Now, this is kind of simple Z standard on a CPU only activity. There's absolutely no accelerator work involved so far. Now I'll do the same test on accelerator using QAT, and you'll see the difference in performance and gain, what kind of gains are we going to get, right? I'll quickly move to the next part of the demo. Here, I'm going to create, before I kickstart the QAT engine, there's something called QAT hardware config. So what it essentially does is, it is going to reset my hardware kind of resources in the CPU. So I'm basically doing it's like more like a service restart, if you want to really call, but it's more at the hardware level. So here I'm processing that. So all the QAT functions are restarted. And when I do a head stop again, there's absolutely no process running, right? That's what you see right now. Now I will go and kickstart the QAT script, which is basically, again, a write function of QAT for the same data size that we did with the non-QAT, Z standard rather. Now it is starting up and it's enabling telemetry. And I will quickly jump on to. So here again, it is starting to run the function. So here one thing to notice is, here you can see the type is now changed from Z standard to more of an Intel QAT compression RocksDB option, right? So which means the compression is now getting offloaded to the QAT engine, and the compression is taking place not on the CPU anymore, but it is going on the QAT engine itself, right? So that's kind of one thing to notice. Now, again, when I do a head stop, I don't see much activity happening yet. So we will continue to move forward. Yeah, here is another interesting thing. There's something called PCM Axle. PCM Axle is a process control monitor accelerator. This is a one way where you can capture telemetry right from the accelerator to understand what's happening within the accelerator. So now that you've offered that function into the accelerator, so you want to know what's going on within the accelerator, right? So this is a kind of a table that you will see, and it'll show what socket it is getting used and how much of bandwidth is going into the accelerator, how much is coming out, and what is the compression percentage in terms of utilization. On 0 and 1. Well, 0 is basically one partition of the accelerator, and 1 is another partition of the accelerator, and you're going to see a mean utilization data that is coming out of it, right? I will continue forward with the testing. As we progress, the test is now started to run, and we will slowly start to see how much of data processing is now going to kick in, right? So the run 1 is started, and it will move forward. Now, we still don't see any activity in the accelerator, but slowly we've started to see some numbers getting populated there. So this is a very interesting thing to start. I'll take a pause here as well. So what it does is basically, you can see there's about 28 to, there's about 19 gig. In some cases, you're getting 41 gig. So there's so much data that is getting pumped into the accelerator itself. And that is able to do about 86% of compression and about 85% of decompression. And here you can see about, again, 83% of decompression on the slice 2, or probably the partition 2, and then about 75% of decompression. So overall, you can see about what percentage of compression and decompression is happening at a utilization level at an average across these accelerators, right? And here you can see QAT 0, 1, 2, 3, 4, 5, 6, 7, 8. So each socket has 4 accelerators. So we have 2 sockets. In this case, we are running 8 accelerators of QAT instance on this CPU, right? That's kind of where we are running. And I will move forward. Here, you can slowly start to see the CPUs getting piped up. But we can see with that function, our CPUs somewhere around about 60-65%. It's not peaking like 94 or 95 that you saw in the previous test about with Z standard, which essentially means you're reaching that CPU saving that one want to do. And also here you can see the latency is now dropping at that amount of compression and decompression happening, right? So there you could see the latency going almost like 1 second or 1 millisecond. 1+ second of data. Here you can see the average is about 600 to 700. In some cases, it's even below 500 milliseconds, right? So this CPU, this microsecond latency variation will make a lot of difference in performance as you progress forward, right? And I will also, you can also see the system load has been under 20% or most of the time. So which means it's not getting kind of overutilized, which indirectly constitute to like a power saving as well, right? Again, this is showing us how much of compression and decompression is running. So as I told you, this is set for 3 minutes. So the test is happening as we speak. So I will move forward to more of a, let me move to, yeah, now slowly the kind of the test is kind of coming to like an end. Yeah, so here, what I'm showing here is, you can see the test is completed. You're getting a similar throughput of about 18 million IOPS, and you got a better data set, which means your data size is getting improved, and your CPU is well under 60% of most of the time, right? So which means you're almost getting about 30-35% of CPU saving, right? So I have a chart to kind of depict that. The next few minutes, let me show that. What happened? Not sure. Yeah, so I exported all this data to like a Power BI to kind of make it more simple. So here you can see with the Z standard method, the CPU was almost 94%, and IOPS or throughput we were able to achieve was about 18 million, 280K. In the case of QAT, we were able to keep that utilization under 60% in most of the cases, and more or less the IOPS remains constant. It's about again 18,605. In terms of the data set size, the data set size with QAT obviously increase a little bit, but it's very marginal differentiation you see. It's about 200 or 20K difference in terms of the data set size. But the key factor to know here is the QAT was able to achieve 35% of CPU savings or core savings, right? Which means with accelerated computing, you see a lot more benefit from running into like for an encrypt or a decrypt or compression or decompression function for an application like RocksDB. So this becomes very critical as more and more applications are today consuming compression and decompression methodologies or functionalities today, right? Most of the common applications which are used extensively, like social media applications or even like music applications, use a heavy amount of compression and decompression methodologies, and QAT comes in very, very handy for serving that purpose, right? So I will switch back to our slide. I want to take a kind of a note where we are heading towards. This is accelerated computing is kind of heading to the future. And one of the key reasons why we are emphasizing on accelerated computing is the next generation of workload deployments are extremely compute sensitive, which means that we need some or the other way of acceleration so that we can achieve that extra performance or for getting that capacity enhancement, growth, and whatnot, right? Which ultimately leads to a bigger factor called TCO or total cost of optimization. So end of the day, every customer is looking at, hey, how do I get my cost below and keep my total TCO value as possible, as low as possible, right? So here I'm giving a very nice depiction of how we are able to save that, right? Today, if you look at the left-hand side, you see the blue boxes are purely running CPUs, and the green boxes are more like appliances with running accelerators. So this is a data center where you're running without an accelerator. The green boxes are like an appliance which is exclusively doing that compression and decompression function outside of the box, which gives you more TCO, more I would say more power, which means more cost, which means more latency and performance degradation, right? So when you shift it at the right side, what you're really seeing is the whole thing is now offloaded within the CPU itself, right? Like how Kalyan was mentioning, this accelerator is sitting part of the die itself. So you're not really leaving your server and going out, whereas your workload acceleration is running in your CPU die itself, right? So, which means I'm able to add more capacity within my data center, which means more racks and more compute for other workloads, and also potentially leading to more CPU savings, which means power savings and better performance. So, in a sense, if you really want to call for accelerated computing and future computing needs like AI and other workloads that are becoming more hot in today's market, we really see accelerators becoming a more and more prominent for kind of next generation workloads and applications, right? So this is where Intel is striving towards, leading towards more accelerated computing. And we have, as Mrittika and Kalyan showcased, we have a whole lot of accelerators and other use cases. We just showed one small example with QAT. We have DSA, we have IAA, and we have like AMX for advanced AI workloads, which is in the future generation of our processors. So we look for. I hope this session was useful, and we look forward to taking up any questions. I know we are almost top of the hour, but we can take any questions for the next 3 to 5 minutes. Thank you for your time. Anybody has any questions? Feel free to ask, open your mic and ask, or you can put that on the Slack channel as well. Hey, moderators, I'm not sure if the participants can unmute themselves. If you want to give an opportunity for anybody to ask question. Thank you.
Yeah. If anyone wants to, if you're unable to unmute, let me know. I'm happy to unmute you. Or if you want to put something in Slack, I'm watching that.
Either we were very good or people don't have any questions. So I don't know. We'll still wait for a few more minutes. And also I'm just going to check the Slack if any questions are there up there as well.
I think we can.
Okay. Hey, Amanda, I'm not sure if anybody has asked anything, but yeah, we'll be online if anybody wants to kind of reach out to us, and feel free to ping us, and we will get back to anyone who's interested in getting to know more about accelerated computing and telemetry. Thank you.
Yes, I have not seen anything in Slack, but we will keep the Slack channel open as well. So if anyone wants to ask in Slack, that channel will stay open. Thank you very much. That was a great talk.
Sure.
Thank
you.
you.
Thanks
Thank
a
you,
lot.
everyone.
Have a nice weekend, everyone. Bye.